the world of probability. Let me get rid of this this calculator. We don't need this. Just use a regular calculator. All right, so first example, and I am recording, that's good. A student is randomly selected from our class. What is the probability that the student is wearing a red shirt or white sneakers? This was a wonderful question when there was a physical class that met, because then it would be like, all right, let's go around the room. Are you wearing a red shirt or white sneakers? Okay, so well, that's not going to fly. All right, so what I'll do is I'll just make up a set of individuals here, and we'll say that there are 5 people. I'll make an example. 5 people with, I'll do red shirts first. Let's say 4 people. I'll keep the numbers reasonably small with white sneakers. Now let me say that there are 7 people with both. All right. So we're kind of just imagining that we're actually in a classroom. I posed this question like I would normally pose it. Looked around the room, you know, just polled everybody. You know, oh, you're wearing a red shirt. Oh, you're wearing white sneakers. You're wearing both. You're wearing neither, you know. And so this is what we would have come up with. All right. So in the form of the Venn diagram, the fact that you could have both, that allows for some overlap. So I'm going to mark up the Venn diagram with these values. All right. So we have our red shirts. White sneakers. And then both. And I think hopefully it's pretty clear what the both is referring to, right? Both red shirt and white sneakers, right? So when I say 5 people with red shirts, because they're not in the both category, those would be people that are wearing red shirts, but not white sneakers, all right? So not wearing white sneakers, I'll put that in parentheses. And the ones that are wearing the white sneakers are not wearing red shirts. You know, maybe they're wearing blue shirts, or there's a nice floral pattern that doesn't include red, you know, so. And, you know, this is a very generic type of question because it's like, does it have to be all red? You know, like, can it be some red? Does it just have to have red in it? You know, like that kind of thing. It's just, you know, it goes into the category of just go with it. Right. So we have 5 red shirts. We have 4 white sneakers. And we have 7 that's both. Right. So if I want to have the probability that a person is wearing a red shirt or white sneakers, then it's the sum of all of these different things, because it accounts for each possibility, right? So, because remember, it's true, an or sentence is true if either part of it is true, right? So, so I'll get into the probability. So probability of red shirt or white sneakers. The sentence is true if either part is true. All right. And so what that means, you know, I'm being a little bit more elaborate, I guess, in my response than I need to be, but this is for more instructional purposes than anything else. And in a lot of cases, you'll just throw the answer down and be done with it. But what this means is that we would want to be finding the probability of getting a red shirt, but no white sneakers. We would want to add to that. I'm going to just kind of shrink a little. I missed the dot. You know, bring it in. There we go. Now I'm going to shrink it all down. And then extreme close-up. All right, so plus the probability of white shirt, but no, oh, sorry, white sneakers. Geez, white shirt. Like, where did the white shirt come from? White sneakers, but no red shirt. And then plus the probability of getting red shirt and white sneakers. That's the overlap. Right, so if we find the sum of these probabilities, then we're in good shape. The only issue is we don't have a denominator, right? Because we don't have everyone else, you know. So that's the big concern. So I got to throw that piece of information in there. So let me say, as part of the condition for the problem, you know, we went around the room. We had 5 people that were wearing red shirts. We had 4 that had white sneakers. We had 7 that were both, and that we had, let's say, 25 people in total, 30 people in total. Because otherwise we wouldn't have a denominator, all right? So when I mark up my Venn diagram, I would take into account that we have, again, 5 people with the red shirts and no white sneakers, but out of something. You know, I'll get to the something in a second. White sneakers, but no red shirt, 4 out of something. And red and white happening simultaneously. So red shirt, white sneakers, 7 out of something. We would find the sum of those probabilities, right? The key is how many people are in total of 30. All right, so that would be my denominator. And so we're looking at 9 plus 7 is 16, so 16 out of 30 individuals would satisfy those conditions. And I just highlight it. It was getting ugly quick. All right, so in terms of the Venn diagram, that leaves a little bit of the segment of the population that hasn't been accounted for. Okay? Now it's beyond what the question's asking, but you know, it's worth talking about a little bit, because if the rectangle accounts for the entire sample space, and I'm telling you that 16 people have been accounted for, then the people that would remain would be the people who are not wearing red shirts or white sneakers. All right, so no red shirt or white sneakers. That's going to be everyone else. All right, so that's all of this space out here. That's all of this stuff accounts for everyone else in the class, the people who are not wearing red shirts or white sneakers. And in total, that is 14 people. All right, so 14 individuals. All right. So when you add up all those quantities together, you get the grand total of 30 people in the class. All right, but it isn't until you consider the entire picture that you realize that all that stuff is happening interchangeably and in conjunction with one another. And you could also kind of look at it and say, well, now with a complete Venn diagram, I'm prepared to answer any question related to these students in class. You know, maybe the question is, all right, well, what's the probability that you're just wearing white sneakers or you're wearing neither? You know, if the question was, what's the probability of students wearing neither a red shirt nor white sneakers, then you would know there's 14 out of 30. All right. All that background information needs to be given to you in order to get started on a problem like this. Sometimes what I like to do is just give a diagram, you know, like just a quick picture of, you know, like a cartoon classroom, you know, people sitting at desks, you know, just cartoon characters sitting at desks. And, you know, some of them will be wearing red shoes and some of them will be wearing black hats, and, you know, and you can determine probabilities based off of that. I like those problems because they're a little bit more relatable than the deck of cards.
Professor,
right. Yeah.
I have a question.
Sure.
You just added the 30 for the total, or what did you add? Are you?
I threw in the 30 because we needed to have a total.
Okay, perfect.
In order to make the problem work, yeah.
All right.
All right, so we're good. All right, so number 2, a person observes a busy intersection with a traffic light for a period of 10 minutes during rush hour. 200 cars for some reason, drove through the intersection during this time. Of those 200, 30 cars ran a red light, 50 cars sped through a yellow light, and 15 cars did both. What percentage of cars did neither? Right, so it's basically the same question, except now you're given a lot of that background information that was kind of neglected because, you know, we're not in a physical classroom together. So we have really 3 concepts here. Well, 2 concepts, and one is the merging of the 2. Right? You're either going to run a red light or speed through a yellow light, or some kind of mixture of those 2. Right? So those are our sets A and B. Ran red light, sped through yellow. And then you just chuck in a both here.
And you don't count both towards left or right, correct?
Correct.
You consider them basically, essentially a third category.
Essentially, yeah.
Cool, thank you.
No problem. All right, so that period of 10 minutes during rush hour, that's kind of just information at this point, but it doesn't have any bearing on the probability, at least the way the question is structured. All right, so 200 cars drove through the intersection during this time. That's like 30 people in a classroom, you know, same idea. All right, 30 cars ran a red light, 50 cars sped through a yellow light, and 15 cars did both. All right, so 30 is the red. Oh, that just jumped on me. 50 sped through the yellow, and 15 did both. All right. Now, the phrasing of these probability questions can be very awkward. On a test, I like to be a little overly specific because, you know, if there is a little ambiguity here where you're like, wait, so is that 30 cards that only ran a red light? Or is it 30 cars that ran a red light with 15, the 15 that did both being part of that 30? The way that this question is intended is that those 30 cars only ran the red light, right? So like there was no yellow, like the light had turned red, then they ran it, right? The 50 cars that sped through the yellow were like, I think I can make it, I think I can make it. And maybe they did, maybe they didn't, right? But they sped through the yellow light, right? And then the other 15 are the ones that did both, where they sped through the yellow light and then the light turned red in the process, causing them to run the red light, right? So structurally, it's like this. Otherwise, you'd run into an issue of like, well, how do I know which part of the 15 is corresponding to which group? So I tend to be on a test a little bit more specific, and I'll say of those 200, 30 cars ran the red light only. I'll throw the word only in there to make it absolutely clear. But for problems on in a lesson, it's not really that big of a deal, right? So we want to know what percentage of cars did either. So it is calling for a percent as a final answer. So we'll have to keep that in mind. It's not like a suggestion. It's a requirement. When it says a percentage, it's calling for a percentage as a final answer. So we got to be mindful of that, right? So what I have here is a total of, looks like 95. So I know that I have 200 cars overall. So 200 cars overall. And then these entries, I'll just highlight, boop, boop, boop. 30 plus 15 plus 50, that's going to get me 95, right? So if I just do a quick off on the side, 200 minus 95, that's going to get me 105, all right? So those are the remaining cars, right? All right, so if we're looking at the cars that are falling into the category of speeding, running red lights, and things like that, as part of that group of 95, and the other 105 have to be everybody else who, you know, maybe they were breaking other laws, but they weren't breaking these laws, right? So we're saying neither ran a red light nor sped through a yellow. That's going to amount for this. So this is this category here. All of this information amounts to that 105. So in terms of detail, appropriate probability notation, what I would normally say is if I were looking for the probability that a person ran the red light or sped through the yellow, the way the notation would look like, it would be this: probability ran a red or sped through a yellow. And again, it's true if either part is true. So that would amount to 30 out of 200 plus 15 out of 200 plus 50 out of 200. All right, so it's 95 out of 200. All right, so that would be the probability that we wouldn't want. All right, so this is what we don't want. So the opposite of that, all right? So the opposite would be the probability of neither, and you know what, I'm going to be a little selfish here. I already wrote it. That's going to be 1 minus 95 out of 200. So you can get your probability that way, which would be still the 105 over 200. Either way, one way is a more visual Venn diagram approach. The other way is a little bit more notation heavy, but they still get the same outcome, right? Now, in terms of like rounding and things like that, we'll get to that in a second. We do need to report a percentage, but we can get the appropriate fraction either way. All right. One way is a little bit more intuitive once you have the Venn diagram. The other way is a little bit more formulaic. Right. So let me just pop it into Desmos here so you can see. If I had 30 over 200 plus 15 over 200 plus 50 over 200. You got that decimal value there. Again, that's the one we don't want. So what I would just do, and you could tap on that little fraction icon there to get it into a simplified fraction form. We don't have to actively go through the process of simplifying fractions. We just, you know, like we'll take them when the calculator gives them to us, though. We could say 19 out of 40, right? If you want to verify it, you can just take a look and see that 95 out of 200 is the same decimal. It's the same fraction, right? So that's fine. So what I would do is I would subtract, I would do 1 minus 19 out of 40. Oops. Tap. And you get the 0.525, or you could have just taken the decimal equivalent. If it's clean enough, that's fine too. You could just do 1 minus 0.475, you get 0.525. Now it's saying what percentage, right? So this is going to be approximately, well, I'll just go with the whole decimal. So 0.525. Then we multiply by 100 to get it into percent form. So 52.5%. And again, we're only putting it in percent form because the question asked us to. If it didn't ask us to, we wouldn't. Right? We would have just left it as the 105 over 200. There's no requirement for simplifying fractions. There's no requirement for putting it into decimal form from a fraction form, unless the question tells you specifically to do it, which it will hardly ever do. All right. So number 3, we're talking about cards in a deck.
One quick
Sure.
question. So
Yeah.
from a process standpoint, it's better to do it this way to find the knowns, right? And then subtract that from the opposite when it gets more difficult, right?
I believe so. Yeah.
Okay, I got you.
All right. So number 3, we're looking for the probability of either a 7 or an ace being selected from a standard 52 card deck. All right. So for that case, you know, I'm going to just grab my deck of cards, a little diagram here, and bring it over just so I have something to point to. Make it like super tiny. You know, because if you have the whole sample space available, it's pretty easy to just count up the ones that you need that fall into the category that you're looking for and then go from there. But sometimes it's a little easier to do it analytically or using the algebraic approaches. So we're looking for a 7 or an ace. Now, the first thing that you would want to account for is the idea of whether or not you could have a card that satisfies both conditions at the same time. So I'm going to write in 7 and ace. All right. Now, looking at the deck of cards, I see my set of 7s over here. And I see my set of aces over here. There's no way that you could have a card that is both a 7 and an ace at the same time. All right. So there is no overlap. All right. So what I do, there's different schools of thought on this. I like to always kind of go into a problem assuming that there's going to be overlap and then be pleasantly surprised when there isn't. So what I'll do is I'll just say no overlap. Just make a little note. All right. You could redraw the circles if you want, but that usually, what I just did there usually just gets the job done for most people. I didn't put my circle draw tool on, so I don't know why I expected it to draw a circle for me. All right, so this is what we would be dealing with if we were to redraw the diagram. That's, in my opinion, a fair amount of effort for not much payoff, So it's like, oh, okay, well, what did this diagram get me that making a simple note that there's no overlap, what did one do for me that the other didn't? I don't know. So, but to each their own. So what we would be looking for, if I want the probability of a 7 or an ace, is the probability of getting a 7 plus the probability of getting an ace. That's assuming you didn't want to just simply count them all up, right? Because looking at the diagram is really all you need. I mean, I highlighted 8 values there. There's 52 overall. So the answer is 8 out of 52. But in terms of understanding the underlying concept, it can kind of make sense for us to at least go through it once or twice. So 4 out of 52 accounts for the 7s, and then another 4 out of 52 to account for the aces. And we end up with a total of 8 out of the available 52 cards. All right. So that's the 4 7s, the 4 aces with no overlap, total of 8 cards. All right. So in my Venn diagram, I would be saying neither 7 nor ace, which would be everything else. All right. So all this other stuff here, again, with the Venn diagram approach, all we're doing is outside the circle, taking into account everything that is not satisfied or is not taken into account by the circles themselves. All right, so that would be a total of 44. So 44 cards. And again, this question, I mean, not again, I didn't say this yet, but this question is more of like a learning experience where you look at it and say, oh, well, I could have done this just by counting. I really like this problem more for the purpose of kind of showing you that all the techniques for probability are going to work, and you can kind of look at it using something that's a little bit more relatable before we get into the more abstract stuff. And you're saying, I have no way of checking to know if this is going to be right. Like this is a little bit more user friendly. All right. But then you come across the next one where you do have some overlap. Diagram there. We got our 7s. And then we have our red cards, all right? There are many cards that are both 7 and red at the same time. All right. Did I say many? There aren't many. There's just 2 of them. But there are examples of cases in which there are cards that are red and 7, all right, at the same time. All right. So what I would do is I would just take note again of all my 7s, and then take note of all my reds. All right. And so what we're looking at here is an intersecting set. All right. We have a set of cards or set of events where there is a commonality. You can satisfy one and the other at the same time. Right. So what this would be again is the probability of 7 plus the probability of getting a red. I'm going to steal my work up here a little bit. All right. But we're going to run into a problem here, because if I just look at those values and say, okay, well, how many 7s are there in a deck? There'd be 4 out of 52. And then I'd say, well, there's 26 out of 52 reds in the deck because half of them are red and half of them are black, and there's 52 overall. You run into a little bit of an issue because we're double counting, you know, because if I just go through and I actually count them all, let me do that using a thick marker here. I'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. And then since I've already counted 2 of the 7s, I don't have to count them again. I just have to count the other 2 7s, so 27, 28. All right, but if I take my 2 fractions here and add them together, I'm going to get 30 out of 52. I should only get 28 out of 52. And that's because what I need to do is account for that overlap, right? Because if I take all of my 7s without making an adjustment and add to it all of my reds, then I'm going to overcount. So this is not going to be a good way to go, right? We can make a slight adjustment, so I'll leave it for a second. But a better way of doing it would be to say we would have the probability of 7 and not red, otherwise known as black, plus the probability of getting red and not a 7. So basically exclusive of one another. So don't count the red 7s at all. You know, so just the 7s that are not red, so just the black 7s, and just the red cards that are not 7, and then add on the overlap. All right, so I'm gonna mark up my diagram again just to show you what would happen if we did it that way. I'll just move this over. Oh, no. All right, so 7, a card that is a 7 and not red. All right, so I would just look through it and I'd say, okay, well, I got a 7 that's not a red. That would be this. Oh, I need a thicker pen. This one and this one. All right, 7 and not red. Then red but not a 7. All right, that's red and not a 7. So is that, and so on. Let's skip over those 7s. So I'm up to 26 total. And then the last thing that I would account for would be the reds and the 7s. So you know, if I'm just going by the probabilities here, I would say I had 2 out of 50. Ooh, that's a little thick. 2 out of 52 for the 7 and not red. Plus, then I would have 1, 2, 3, 4, 5, 6. We're looking at 24 out of 52. Count them all up. And then the last little category there would be just the red 7s. There's only 2 of those. So notation wise, we're able to come up with the answer that we expected of 28 out of 52. All right. But then the big question would be, and maybe it's not a big question. I don't know. It would be a big question if I were in your position, where I'd be looking at it and saying, all right, well, what about that probability of 7 plus probability of red? We were onto something there. I got pretty close to the final answer. Is there some slight adjustment that I could make to that in order to get the answer without doing all this work? And the answer is yes. All you'd have to do is subtract off the overlap. The cards that are 7 and red at the same time. All right, the ones that were double counted essentially. All right, so I would subtract off the 2 out of 52, and that would give me a result of 28 out of 52. And all of that is operating under the assumption that you don't want to just simply count up the values in the set and create a Venn diagram out of it. You know, you want to have some formulaic approach. You know, this is one of those situations where maybe you don't care because there's not a whole heck of a lot of work involved in doing the counting. But if it gets a little bit more involved, like the data set gets larger, instead of having 52 values, you got 520 values, then you're going to want a different way, right? So marking up the Venn diagram, a 7 card that is not red, there's only 2 of those. Red 7s, there's 2 of those. And red cards that are not 7s, like I said, there's 24 of those. So that gives us everything that we need, and everything outside of that would be neither red nor 7. And that would amount to all this other stuff here. Which is every other card in the deck. All right, so we got 28 out of 52. That would be what, 24. I think, yeah. So 24 cards that are neither red nor 7. So there's a lot of ways to look at probabilities when it comes to an or situation. Some, you know, like easier than others, and the flexibility to bounce between one approach and another approach, because you know the tendency is, especially with math, is like, just show me one way that's going to work and let's just move on from there. Like that's the way we all want it, you know. But sometimes, you know, the diagram approach is going to work when you have a card type problem, whereas a formulaic approach is going to work for something a little bit more abstract. You know, those are some other possibilities that you know that you want to have in mind. And if the numbers get really out of hand, then you want to get technology involved. You know, you don't even want to use a formula or a diagram. You want a computer to figure it out for you. All right, so there's a lot of ways around. A lot of ways to navigate around probability. All right, so in the interest of not keeping these videos too long, I'm going to stop the recording here.